NENOMATICA, where mathematics meets YouTube excellence. Today we're going to learn how to evaluate functions with multiple variables by substituting values and working step by step. Let's start with our first example. This is a function f with three variables, a, b, and c. The function multiplies two expressions together. First, the sum of a, b, and c, and second, a more complex expression involving squares and products of these variables. We need to evaluate this function when a equals 2, b equals 1, and c equals -3. Let's substitute these values into our function. First, I'll substitute these values into the first parenthesis, a plus b plus c. We get 2 plus 1 plus -3, which equals 0. Now, let's calculate the second part of the expression. We have 2 squared, which is 4, plus 1 squared, which is 1, plus -3 squared, which is 9. Then we subtract 2 times 1, which is 2, subtract 2 times -3, which is -6, so we're adding 6, and subtract 1 times -3, which is -3, so we're adding 3. Adding all these terms, for plus 1 plus 9 minus 2 plus 6 plus 3 equals 21. Now, we multiply the two parts together, since the first part equals 0, and 0 multiplied by any number is 0. Our final answer is 0. Now, let's move to our second example. Here we have another function with three variables, but this is the quadratic formula, which gives the solutions to a quadratic equation. We need to evaluate this function when it equals 4, b equals -4, and c equals -3. Let's substitute these values into our formula. First, we replace a with 4, b with -4, and c with -3 in the formula. Now, let's simplify this expression. Negative of -4 is +4. In the square root, we have -4 squared, which is 16 minus 4 times -3. That's 16 minus 4 times -3, which is 16 minus -48, or 16 plus 48, which equals 64. In the denominator, 2 times 4 equals 8. The square root of 64 is 8. So we have 4 plus 8 in the numerator, which is 12 divided by 8. Simplifying 12 divided by 8, we get 3 divided by 2, or 1.5. Therefore, f4 minus 3 equals 3 over 2. To summarize what we've learned, when evaluating functions with multiple variables, we 1. Substitute the given values into the function 2. Simplify each part step by step 3. Combine the simplified parts to get the final answer. In our first example, we found that f2, 1 minus 3 equals 0. In our second example, we found that f4 minus 3 equals 3 over 2. Practice these steps with different functions to become confident in function evaluation. Welcome to our math video. Today, we're going to solve a nested exponent expression. Our function is f of a, b, c, d equals a raised to the power of b, and that entire quantity raised to the power of c raised to the power of d. We're given the following values. Equals 10, b equals 2, c equals 3, and d equals 2. Let's substitute these values into our function. We get f of 10, 2, 3, 2 equals 10 raised to the power of 2, and that entire quantity raised to the power of 3 raised to the power of 2. Now, let's evaluate this expression step by step. First, we'll calculate the innermost expression, 3 raised to the power of 2, which equals 9. Now we can substitute this value into our expression. We have 10 squared raised to the power of 9. Next, let's compute 10 squared. 10 squared equals 100. Substituting again, we get 100 raised to the power of 9. Instead of calculating 100 to the power of 9 directly, let's use the laws of exponents to simplify this expression. We know that 100 equals 10 squared, so 100 to the power of 9 equals 10 squared times 9, which equals 10 to the power of 18. Therefore, the final value of our function f of 10, 2, 3, 2 equals 10 to the power of 18. Let's understand the pattern we followed. We worked from the innermost expression outward, first calculating c to the power of d, then using the result as the exponent for a to the power of b. We also used a key law of exponents. When we raise a power to another power, we multiply the exponents. This allowed us to simplify our final calculation. In this video, we'll solve a geometry problem using Heron's formula to find the area of a triangle. Let's take a look at our example. We have a triangle with sides a equals 6, b equals 8, and c equals 10. To find the area of a triangle when we know all three sides, we'll use Heron's formula. This formula states that the area equals the square root of the semiperimeter times the semiperimeter minus each side. Let's start by calculating the semiperimeter P. By definition, the semiperimeter equals the sum of all three sides divided by 2. Now we substitute the values of A, B, and C into the formula. P equals 6 plus 8 plus 10, all divided by 2. 6 plus 8 plus 10 equals 24. 24 divided by 2 equals 12. So our semiperimeter P equals 12. Step 2. Now we can apply Heron's formula using our calculated semiperimeter. The area south equals the square root of P times P minus A times P minus B times P minus C. Substituting our values, we get south equals the square root of 12 times 12 minus 6 times 12 minus 8 times 12 minus 10. Step 3. Now let's simplify the expression inside the square root. 12 minus 6 equals 6, 12 minus 8 equals 4, and 12 minus 10 equals 2. So our expression becomes south equals the square root of 12 times 6 times 4 times 2. Let's multiply the numbers inside the square root. 12 times 6 is 72, and 72 times 4 is 288, and finally, 288 times 2 is 576. The square root of 576 is 24. Therefore, the area of our triangle is 24 square units. So using Heron's formula, we've calculated that the area of the triangle with sides 6, 8, and 10 is 24 square units. This formula is particularly useful when we know the three sides of a triangle but don't have information about angles or heights. Remember, Heron's formula works for any triangle as long as you know all three sides. Try applying it to other triangles to practice. Thank you for watching. Welcome to our mathematics video. Today we'll solve an algebraic problem involving exponential expressions. Let's look at our problem. If we have the equation where a plus 1 raised to the power of 20 plus b minus 1 raised to the power of 20 equals 0, we need to find the value of the expression a squared minus b squared raised to the power of 2000. Let's start by analyzing our first equation. Notice that when any real number is raised to the power of 20, the result is always non-negative. So we have the sum of two non-negative terms equaling 0. The only way this can happen is if both terms individually equal 0. Since we have a plus 1 raised to the power of 20 equals 0, that means a plus 1 itself must equal 0. Similarly, since b minus 1 raised to the power of 20 equals 0, b minus 1 itself must equal 0. Therefore, a equals -1 and b equals 1. Now let's calculate a squared minus b squared raised to the power of 2000. First, we substitute our values. A squared equals -1 squared, which is 1, and b squared equals 1 squared, which is 1. So we get 1 minus 1, which equals 0. And finally, 0 raised to the power of 2000 is still 0. Let's summarize our solution. We started with the equation a plus 1 to the power of 20 plus b minus 1 to the power of 20 equals 0. Since these are both non-negative terms summing to 0, they must each be 0 individually. This gave us it equals -1 and b equals 1. When we substituted these values into a squared minus b squared raised to the power of 2000, we got a final answer of 0. This problem demonstrates a key principle in algebra. When working with high powers, we can often find simplified approaches by analyzing the fundamental properties of the expressions. Welcome to our math lesson today. We'll solve a challenging algebraic problem involving exponents and substitutions. Let's begin with our example. We have an equation with exponents and need to find the value of a specific expression. Let's analyze our equation. We have the sum of two terms equal to 0. Notice that both terms are raised to even powers, 50 and 100. This is a key insight for our solution. Here's an important rule to remember about even powers. Since both terms are raised to even powers, they are always greater than or equal to 0. For their sum to equal 0, both terms must individually equal 0. Now, let's solve for the variables. From the first equation, a minus 4b equals 0, so a equals 4b. From the second equation, b minus 2c equals 0, so b equals 2c, which means c equals b over 2. Let's substitute these values into our target expression. 10a be divided by c times the quantity a plus b. Now let's substitute c equals b over 2 into our expression. To complete our calculation, we divide 40b squared by 5b squared over 2. When dividing by a fraction, we multiply by its reciprocal. This gives us 40b squared times 2 over 5b squared. Therefore, the value of our expression is 16. Let's review the key steps we followed to solve this problem. In this video, we'll solve a problem involving quadratic functions. We need to find the value of a function at a specific point, but first we need to determine the missing parameter in the function's definition. Let's begin by understanding the problem statement. We are given that f of 1 equals 7, and that the function f of x equals ax squared plus x plus 4. Our task is to find the value of f of negative 3. Let's start by finding the value of the parameter, a. We'll use the given condition that f of 1 equals 7. We know that f of 1 equals 7. Let's substitute x equals 1 into the function definition. F of 1 equals a times 1 squared plus 1 plus 4. This simplifies to a plus 5 equals 7. Now, we'll use the basic algebraic property to solve for a. Subtracting 5 from both sides, we get it equals 2. Now that we know it equals 2, let's write the explicit form of our function. We'll substitute at equals 2 into our original function definition. Our original function was f of x equals ax squared plus x plus 4. Substituting at equals 2, we get f of x equals 2x squared plus x plus 4. Now we can find f of negative 3. We'll substitute x equals negative 3 into our function. Let's substitute x equals negative 3 into our function f of x equals 2x squared plus x plus 4. We get f of negative 3 equals 2 times negative 3 squared plus negative 3 plus 4. First, let's calculate negative 3 squared, which is 9. So we have 2 times 9, which is 18, plus negative 3 plus 4. 18 minus 3 plus 4 equals 19. Therefore, the value of f of negative 3 is 19. To verify our answer, we can check that when we substitute our value of a equals 2 and x equals negative 3 into the original function, we indeed get 19. To summarize what we did, 1. We used the condition f of 1 equals 7 to find that it equals 2. 2. We substituted this value of it into the function definition to get f of x equals 2x squared plus x plus 4. 3. Finally, we evaluated the function at x equals negative 3 to get f of negative 3 equals 19. This approach of finding unknown parameters first, and then evaluating the function is a common technique in mathematics. How to solve problems by evaluating functions with different inputs. Let's start with our first example. We have a function f of x equals 1 minus 2x, and we want to find f of x minus 1. To solve this problem, we need to substitute x minus 1 into the function f of x. Let's substitute x minus 1 for x in the original function. Now, let's use the distributive property to expand this expression. We get 1 minus 2x plus 2. Finally, let's simplify the expression. 1 plus 2 gives us 3, so our final answer is 3 minus 2x. Now, let's move on to a more complex example. We have a recursive function f of n equals f of n minus 1 plus 4 times n cubed. We need to find the value of f of 1 minus f of negative 1. For this problem, we need to find f of 1 and f of negative 1 separately, and then calculate their difference. Let's start by using the recurrence relation to find f of 1. Similarly, let's find f of negative 1 by substituting n equals negative 1 into the recurrence relation. Now, we substitute negative 1 for n. Now, we can calculate f of 1 minus f of negative 1. We substitute the expressions we found for f of 1 and f of negative 1. Now, let's simplify this expression. We can distribute the negative sign and then combine like terms. So we've solved both function problems. For the first example, we found that f of x minus 1 equals 3 minus 2x. For the second example, we discovered that f of 1 minus f of negative 1 equals f of 0 minus f of negative 2 plus 8. These examples demonstrate different techniques. We're given that f of x plus 2 equals 3x minus 1, and we need to find the expression for f of x. Our goal is to find f of x. The challenge is that the given equation has f of x plus 2 on the left side, not f of x. To solve this, we can use a substitution method. We need to substitute x with x minus 2 in the original equation. This will transform f of x plus 2 into f of x. Step 1. Let's replace x with x minus 2 in the original equation. F of x plus 2 equals 3x minus 1. When we substitute x minus 2 for x, the left side becomes f of x minus 2 plus 2, which simplifies to f of x. And the right side becomes 3 times x minus 2 minus 1. Step 2. Now, we simplify both sides of the equation. On the left side, x minus 2 plus 2 simplifies to just x, so we have f of x. On the right side, we distribute the 3 to get 3x minus 6, and then subtract 1. Step 3. Finally, we combine like terms on the right side. Negative 6 minus 1 equals negative 7. So our function is f of x equals 3x minus 7. Let's move on to our second example. In this problem, we're given that f of x equals x squared plus 2, and we need to find f of x minus 1 over x. In this case, since we already know what f of x is, we can directly substitute x minus 1 over x into the function. This is different from our first example, where we had to solve for f of x. Step 1. We substitute x minus 1 over x into the function f of x equals x squared plus 2. We replace every x in the function with x minus 1 over x. Step 2. Now we need to expand the squared term. Using the algebraic identity that a minus b squared equals a squared minus 2 of plus b squared, we expand x minus 1 over x squared. When we square x minus 1 over x, we get x squared minus 2 times x times 1 over x plus 1 over x squared. This simplifies to x squared minus 2 plus 1 over x squared. Then we add 2 as required by our function. Step 3. Finally, we simplify by combining like terms. Negative 2 plus 2 equals 0, so these terms cancel out. Our final result is x squared plus 1 over x squared. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.